Okay, so I have pulled up the K-Review, Inference for Differences, and also on the left here, I have the Google Jamboard with notes that you might want to use to as you prepare for your test. So let's start with the first question. Oops, actually, let me go ahead and take off the key because that takes some of the fun out of it, right? All right. So the first question is, a research report describing the results from a repeatedly measured study states that your t-value with 22 equals 1.71 and your p-value, your test statistic is 1.71 and your p-value is greater than 0.05. So if it's greater than 0.05, we're definitely failed to reject. So it's one of the two failed to reject. And then you notice here it says how many participants. So we haven't really done notation like this, but obviously this has to do with degrees of freedom. So we would say 23 participants because degrees of freedom is the number of participants minus 1. And if you look at it on the mean difference for paired data, here I have it, degrees of freedom equals n minus 1. Okay, so we'll go ahead and choose 23, and we're failing to reject. So if you have a set of 20 test scores, your degrees of freedom are 19, okay? So you do 20 minus 1. And then here for repeated measures, experiment comparing two treatment conditions. So I guess it's doing the same sample size. The degrees of freedom is 10, so your sample size is 11. So you just need to know that degrees of freedom is always one lower than your sample size. Now, if we had the following is true for repeated measures of the t-statistic, it's the same number every time, so you would just say degrees of freedom is n minus 1. So, assuming that the sample mean difference is held constant, which of the following data, so I'm on question 6 already, guys, which of the following sets of data is most likely to produce a significant test statistic? So, the more precise you are, so the bigger your sample size, so it's either this one or this one, and this looks like that's supposed to be standard deviation. The tighter the standard deviation and the bigger the sample size. So let me go ahead and do a check on this, just see how we're doing. Submit for testing, make sure I'm right on that last one. All right, there we go. So far, so good. So that's questions 1 through 6. Again, the main thing is to remember that degrees of freedom equals n minus 1, or n is degrees of freedom plus 1. All right, and you also want the smallest standard deviation and the biggest sample size for this one. Okay, when are two random samples independent? Basically, they should be independent if one does not affect the other. Let's see. Well, this is definitely not independent if each data value can be paired. It doesn't matter who the researcher is. If at least some data can be paired, no. If sample data drawn from one population are completely unrelated. So two random samples are independent if sample data drawn from one population are completely unrelated to the selection of the data from the other population. So no pairing, okay? When are two samples dependent? That means that one sample, there should be like a linkage. So two random samples are dependent if the same researcher has nothing to do with researcher. If each data value in one sample can be paired with a corresponding data value. So think of it like when we did correlation, 1x tends to go to 1y. So that's dependent. Okay, so let's go ahead and I'll go ahead and submit since we're about to start a long problem. And we're going to need our staplets. Okay, so coming on down, everything's right. You have a bunch of data here, nothing to fear. There are a couple different staplets. You have one quantitative variable, multiple groups. Actually, I don't need this one. You have one quantitative variable where you put the data in. So let me go ahead and edit the inputs. All I did was, so I want multiple groups because there's two groups of data here, right? And they're not paired. You can tell partly because they're not the same number of data sets. And you don't want paired anyways because you have to do some extra math. So if I take all this and paste it in there, and I take all this and paste it in there, I should be able to begin analysis, right? And there's my data sets. Oh, there's a really big one, 26, right? Must be a 26 in here. Is there a 26 or is that a typo? Ah, there's a 26. Okay, so you can come down here and see the summary statistics. So always good to enter these first. Make sure you're looking at the mean. It says round your answer to 2 decimal places. Technically, I could probably do 0.415 because it'll round for me. And then standard deviation, 2.08. Pretend I'm typing in the right numbers. So that's standard deviation I got from right there. My X bar 2 is 10.65. Oh, I am not putting my fingers on the right keys. 10.65. And then my standard deviation is 3.03. I'll put 2.7 or 2.8 just so it comes out. So let's go ahead and make sure you always have these stats first correct, just in case you did not paste your data well. Maybe you missed a data point, so let's submit that for testing. So these are all correct, so we're golden. And we come down here for inference, and we're doing an interval. How do I know? Because they're looking for a lower limit and an upper limit. You look here, double check your confidence level. It is 95%, and always pick conservative degrees of freedom. It's probably going to default to no, so you probably need to make sure you change that to a yes. Perform inference, and I got negative, let's see, how many decimal places do they want? Negative 0.0695. We'll see if it takes it with all 4. Usually the staplets, the WebAssigns don't mind extra decimals, usually. Let's see how they do. And voila, see, I told you they don't usually care. If they do, then you can come bug me if you're having rounding issues. So looking at the confidence interval, what does it mean in the context of the problem? Does the interval consist of numbers that are all positive, all negative, of different signs, like positive, negative, at the 95% level of confidence? Is the population mean soil water content of the first field higher than that of the second? So if it was higher, we would expect this to be all positive, right? So because this contains both positive and negative values, that means there could be zeros, one of the plausible values. There could be no difference. For our work, we are never using the standard normal, and the reason we don't use it, the reason we don't use it, we use students T instead, is because our standard deviations for the population, these sigma symbols, are unknown, all right? Do you need information about the soil water content distributions? Let's see. Well, let's see, how big are my samples? Samples are, let me look over here. Here's 72 and 80. I actually don't, because I have really big number of samples. So actually I'd say no assumptions are needed, because if you look at the distributions, they're kind of over here on the left, they're kind of a nice lump of data. There are no obvious outliers, and you could check that by doing a box plots. Oh, I do have an obvious outliers, all right? But my samples, actually, it doesn't matter. Outliers are only an issue if my samples aren't big enough. So if these were tiny samples, like 20, then that outlier would definitely be an issue there, and that one might be too. But because our samples are so big, we don't need to do any assumptions. So let me make sure I said that correctly. Let me submit. Let's see. Yeah, no assumptions are needed. And that's basically because we can look at the data and see what it is. Of course, we're assuming these are randomly collected. Yeah, independent random samples. So you're fine there. All right, using alpha equals 0.01 to test the claim that the population mean water content of the first field is higher than that of the second. So what I'll come down here, I need to do a hypothesis test, 2-sample t-test. We believe that mu1 is higher than mu2. So we perform the inference, and then you can see the test statistic and the p-value. Actually, I kind of jumped ahead because I haven't even done my level of significance, 0.01. And we think mu1 is greater than mu2, but we need an equals first, so it's this one. Mu1 equals mu2 for the null. Mu1 is greater than mu2 for the alternate. Sample test statistic is 1.8277, and the p-value is 0.0359. Sampling distribution, we want something shaded to the right, and that appears to be the only one that's solely shaded to the right. Our p-value is greater than 0.01, so we fail to reject because we don't have significant data. And fail to reject, the evidence is insufficient. So we'll go ahead and finish submitting this. And we have a good chunk done. Okay, so let's go. This should all be good. Voila, all correct. All right, now here's one where we have two groups and we have statistics given to us. So what we're going to want to do is we actually want this one. Let me go ahead and edit inputs, but this time I'm going to say mean and standard deviation. And we're still using X1 and X2. This time we're doing average weight. And we have two kinds of wools we're looking at. We're looking at Canadian wools. And the mean is 100 pounds. The standard deviation is the S1, 6.7. Sample size is 20. The other one is Alaskan wools. And their mean weight is 92 pounds. Pickings must be slimmer in Alaska. That kind of makes sense. And their standard, so I got the standard deviation, and there are 25 of them. Do not mix these up. Make sure this is sample size here on that third column. Standard deviation in the middle and mean in the first. So it jumps straight to inference, and it wants a confidence interval. Let's see, what do we want? 75%. That's very unusual. 75%. All right. And we want, always assume conservative degrees of freedom. Make sure that that is a yes. Perform inference, and I can put in my 5.5506, 10.4494. Should not matter that I put in too many decimals. And let's see how we're doing. Oh, voila. See, I told you. All right. So our interval is completely positive. So it only contains, isn't this nice? It makes it super easy to answer this one. We're pretty confident, 75% confident, that Canadian wolves weigh more than Alaskan wolves. So now we're actually going to do this as a hypothesis test using an alpha of 0.01. And we're going to test the claim that the average weight of adult male wolves from the Northwest Territories is different. All right, not more, even though we saw that we can see that it appears to be more. Now we're just testing difference. So we need one of these two difference. It must be on the alternate, and we need an equals on the null. We are going to use a student's t distribution because we don't know our sigmas, and we're assuming that the distribution, the difference has a normal distribution, all right? So that should be right. Students T, we do not know them. Both populations are approximately, we're going to do both populations are approximately normal. And sigma 1 and sigma 2 are unknown. So we need both populations here. If this was just an individual difference, I would do that one. So we're using students T. Both populations are approximately normal, and the sigmas are unknown. What is the value of the sample test statistic? So let me make sure. Remember, this alternate is critical for getting this right. So let's pick a test on the staplet, and we're keeping it conservative, and now we're just saying doesn't equal 0, and we perform inference. All right, so it gives us 3.8756. And if p-value, I'm going to put 10. Hopefully it's going to go. I'm a little worried because that's a little low on the p-value, and the staplet might get funny on me. So let's check that. It's super low p-value. All right. It took it. Wait, no, hold on. Let's see. Did it take? I got to get to the right one. Here we go. Yes, we're good. We're good. So if it says 4 decimal places and you have 0.0010, just go ahead and assume it's a 0 or something. If it's being a problem with a really low p-value, come bug me, show me your answer, and I can check it for you. If you're doing things right, I will give you credit. So since we're looking for different, we need both sides of our sketch to be shaded. So you can see how that's pointing to 2 p-values, so you can tell which one it is. And because it's super tiny, you really can't see it in the picture. Okay, Since the p-value is super tiny, we're going to reject. We definitely have statistically significant data. Since we reject, we have sufficient evidence that the mean weights of the wolves are different. So let me go ahead and finish that one. Hit submit. Okay. And there we go. All good. Everything checked. And let's start on the next one. Okay, so this is, notice a study considered the question, are you a registered voter? So your answer on this is categorical variables, all right? So that means you want the one categorical variable, multiple groups. That's the steplet you want, okay? So if you look at this, we have two methods. We have face-to-face interview. Ignore this. I started doing it for wolves, but it wasn't right. That was quantitative. Face-to-face, and then the other one is telephone. So those are, and then we look at the proportion. Two methods of surveys were used. Are you a registered voter? A random sample of 92 people were asked the question face-to-face. 78 gave accurate answers, and then another sample with 82 were asked during telephone. 73 gave accurate answers. Assume the samples are representative. Note for degrees of freedom. Use the DEF that's close, that is smaller. So this means conservative. If it says something like that, they want conservative, which is what we're doing for the whole thing. In some cases, this choice will increase the p-value by a small amount. But actually, with proportions, we don't usually have to worry about conservative degrees of freedom. So we're going to say here, they say they're registered. Actually, I'll just change this to yes, because the variable is registered voter. Okay. Pretend that. And this is no. So my first sample, face-to-face interviews, we had 78. We're actually saying accurate. So accurate answer. It's not if they're registered, it's if they answer truthfully. So the accurate answers were for 78 out of 92. 92 minus 78 is 14. All right, and we'll double check our sums when we do that. For the telephone people, we had a sample of 82 and 73 of those out of 82. So we only had 9 that were not accurate. Begin our analysis, and you can see our data display. Let's make sure. 92, yes, that's how many we have in the first sample, and 82 is how much we have in the second. So always double check this because it's easy to make a mistake in setting this up. And we want a confidence interval. So I'm going to do a z-interval. It's the only interval you'll see, so it's pretty easy. And we want 95% confidence, and who answered the question accurately. So that we want the yes. And we want an interval for the difference. So let's go ahead. We're ready. Should be okay. Let's check it. It always makes me a little nervous when it does that. It didn't used to do that so often. So let's make sure this is going okay. This should be. It could be because we got a 9 in the original data, and it doesn't like that. So let's see where we are. Yeah, so it's fine. It's fine. All right. So yeah, this warning message, it's just giving us a warning. Does the interval contain numbers that are all positive, all negative, or mixed? It's mixed. So it's got to be this one, right? There is no significant difference because 0 is a plausible value. So that's the correct answer there. Test the claim that there is a difference. So that means it can go either way. And our alpha is 0.05. All right, so this one's not saying higher or lower. It just says there is a difference. So I'm going to do 0.05. And we're going to assume they're equal, but we're wondering if they're not equal. We're going to use these. Okay, so for proportions, we always use a standard normal. See how there's no t here? It has a z. That means it's the student's normal distribution. T distribution would have a t instead of a z. All right, so we're using standard normal. And let's see, we'll use both population distributions are approximately normal, and sigma 1 and sigma 2 are known. Actually, we're going to say the trials are sufficiently large. Let's try that, because we don't really know the sigma. We got to calculate it, right? And we're based on a sample. So let's submit for testing. I want to double check that piece. Did I put 0.06? Bad teacher. That was supposed to be 0.05. They should match. And we're good there. Okay, so what's the value of the sample test statistic? Let's go ahead and do a z-test. All right, perform inference. And again, it's still giving us that 10. You have 9 in one of those. That's not greater than 10. Yeah, I know. Remember that sometimes for your class, it's frequently the value of 5 is considered big enough. In most stats, including our AP class, we tend to do 10 successes. So that's why we're getting this message right here, but this problem with your book is fine. All right. And then this is two-sided. Our p-value's pretty high. Is that right? Let's go double check. Well, actually, look at this. Look at the shading. That's a hint to you too. That's a lot shaded. Is that 80% shaded? I'm not so sure about that. P1 minus P2, we'll see. All right. And the p-value is definitely higher, so we're going to fail to reject because we don't have significant data. And there's insufficient evidence, so we're failing to reject with insufficient evidence. So let's go check this one. We're almost done. We're looking for the one with the really high p-values. Yeah, that's the right p-value. That doesn't feel like 80% to me, but oh well, so I'm not worried about it. Okay, and question 12. Let's see, how many of these do we have, just out of curiosity? We got, okay, we'll have 3 more left. Question 12. Question 12. So this is another proportion, because you can see I'm counting, right? So we'll want this again. And this time, we'll edit our inputs. A researcher studied the accuracy of responses on questions involving sensitive material from public records. Individuals were identified as having been charged with drunk driving not less than 6 months or more than 12 months from the starting date of the study. 2 random samples from this group were studied. In the first sample of 36 individuals, the respondents were asked in a face-to-face interview if they've been charged with drunken driving in the last 12 months. Of those interviewed face-to-face, of the 36 interviewed face-to-face, 17 answered correctly. So this is sort of, and how do we do the second sample? Telephone again. Oh, so it's just like the last one. So we said 17 answered accurately, which means 19 did not. And then the 23, oh, wait. 23, the second sample is 44. That's your N. This is 23. So we're going to say 23 out of 44, so that's 21. And we begin analysis. All right, so there's our accurate and inaccurate. Make sure we add up to the right sample sizes, 36 and 44. So we're good. Now we're going to do a confidence interval, a 90% interval. So let me make sure I do that. Z interval, 90%, perform inference. So my lower limit is negative, and my upper limit is positive. So our interval contains positive and negative values. So far, that's all we've had, isn't it? So we can conclude there may not be any difference in response. Then they say, okay, let's do a hypothesis test, and we're just checking for a difference, not that one is higher than the other. So we're going to have 0.05. And we want equals for our null and not equals for our alternate. We're definitely using a normal distribution because this is proportions. And the number of trials is large. That's mainly the issue there. And let's go ahead and do the test. So what is the value of the sample test statistic? Come here. We are doing not equals to. Make sure you have the right test statistic. Oh, there we go. I was like, is that an interval? No, it's not. So my actually, usually if it's not different, it's going to want a positive z-score here. We'll double check that. And then I can put this. All right. So when it's a not different, this not equals, use the positive z-score. Let's see if I'm right about that. I'm just talking about how the software works. So WebAssign is going to assume the positive z-score, because why would you give it the negative if you also have a positive? It just wants to know how far away it is. And where are we? Voila, voila, voila. That's still old. There we go. Oh, it did want the negative. All right. Oh, it's the sample was lower. Bad teacher, 0.4495. Right. The test statistic comes from the sample. I'm thinking critical values. I don't know why. For hypothesis test, just use the positive statistic. This is why I check. Yeah, for hypothesis test, use what Staplet gives you. It's confidence intervals where we just use the positive. All right, there we go. That should be, oh, now I got to pick, not equals to. You have a pretty high, see, this one looks like better shading. That looks like 65% or more of the area. And so we want not equals to, so you want two sides shaded. We have a very high p-value, so we fail to reject. Our data is not significant. We fail to reject because there is insufficient evidence. And we'll finish with that one. Okay, so now this is one where you're going to have a paired difference of data. So in case you don't have a calculator, here's something you can do. So let me go ahead and delete all this. So what I did, I'm going to show you how to do this on a spreadsheet to make the subtraction easier. Put all your before values. Now, actually, you could do it just like this. Let me set it up a little different than before. All right. So we'll set this up just like them. Store 1, 2, 3, 4, and 5. Right. And here's the before, and here's the after. So I'm going to just type in the numbers exactly the same. 51.7, and your numbers may be different than mine. So keep that in mind. 49.2, 77.4, 43.2. And then I have 67.8, 100.8. If you hit the tab key, it goes across horizontal. 81.2 and 41.9. So the easiest thing you can do, B minus A, that's what we're trying to figure out. You put an equal sign here, and you say equals that minus, whoops, that. And you can actually click. This is Google Sheets. All of you have access. There are your answers. And guess what? You can actually copy, Control-C this. And we're going to go to a one quantitative variable. And our inputs, paste them in here, begin analysis. And there they are, all right? So what are we testing in this problem? It is a paired difference is what we're checking, because this is store 1. Both these data sets go together. This is store 2. That's store 3. So it's paired data. Alpha is 0.01. It may be different for you. And what are we thinking? The consultant, what are they thinking? We're recorded. Do the data indicate that the average net sales improved? So that means the difference, now, and they told you the difference is before minus after. Before should be lower than after, so when I go before minus after, it should be negative. So I'm going to have an equals and a negative. We do not, this is mean differences, right? So it's students T, and we got to assume that the distribution here is approximately normal, not uniform. So it's students T because we're doing a difference. And how can you tell? Later when you come down here, look on the Staplet. You do see some other stuff, but you see the T interval. You don't see the Z. So that's a hint to you that this is students T. Sample test statistic. Let's do a one sample t-test from you. And in this case, the hypothesized mean is always 0 because we have paired differences and we want to see if they're like less than 0 or greater than 0. So here we said less than 0. Always pay attention to your alternate hypothesis. Perform your inference. Negative 2.0673 and 0.0538. Okay. And we are doing less than 0, so I need a left-sided shading, that one right there. And because our p-value is actually lower than 0.10, we reject because we have statistically significant data, and there is sufficient evidence to conclude the sales have improved. Good news for the store. And down to our last problem after I check all these answers. Almost there. So there's our paired differences, and make sure I got everything right. No silly mistakes. We're all good. Oh, another paired difference. So let's try that trick again. So here, I'll just go to my spreadsheet, and this is twin pair. So I can just type over it, twin pair. And A, B, C, D, E, F. So it's got one more set of data than before. 56, 38, 11, 25, 33, 47. And then I'll put 39, 22, 7, 18, 21, 42. Now you're probably going, wait a second, what happened? I don't have all my formulas. Drag this over one extra. So you just basically, again, to set this formula, you go equals. Make sure you're on that cell. Actually, it has the whole thing. So let me delete this for a second. Escape, just so I can show you. Delete. All right, so when I go equals, pretend I put equals. I have a minus equals, that's why it's being weird. Equals. We're going to say the top one minus the bottom one, and that's how it works. All right, so we have all our data. So we can go to the one, we're doing a paired difference. And we go to one quantitative variable, single group. And this is the one where you paste the data in. Voila, there's all my data. Begin my analysis. That's okay. It's fine. Begin analysis. All right. And what is the level of significance? Oh, they told us 0.01. So they're being very picky on this one. And you can see, actually, the differences are all positive. Is that right? Let's see. They sure are. So I have the feeling we're definitely going to get that. And do the data support the claim that the program did promote creative problem solving? So let's see, what are we looking at? The one child was taken at random from each pair to form an experimental group. These children participated in a program designed to promote creative thinking. The other child was part of a control group that did not do that. A creative problem solving test was given with results shown. So our hypothesis, do the data support the claim that the program of the experimental group did promote creative problem solving? So that means this value should be higher than that value. So we're going to assume our differences are greater than 0 for the alternate. Remember, the null is always the equals. These are means. How can you tell? This is t-distribution. See how you don't see any z's right there? So I'm going to go ahead and say the student's t. We're going to assume the difference is approximately normal. We never do this uniform thing. And let's go ahead and do our test statistic. One sample t-test from you. We think the difference is greater than 0. And our test statistic is 4.4184. And our p-value is 0.0035, which is very tiny. We want a graph drawn to the right, so we'll take that one. And we're definitely rejecting. We have significant data because our p-value is 0.0035, which means there is sufficient evidence, and we submit for testing. And we should be done. All right, we're all good. Yeah, everything's right. Well, good luck on your test. And don't forget to make your cheat sheet.